All right, so another great earthquake destruction cause or effect are tsunamis. So major undersea earthquakes may set in motion a series of large ocean waves that are known by their Japanese name, which is tsunami, and it literally means harbor wave. So most tsunamis are generated by the displacement along a megathrust fault that suddenly lifts a very large slab of the seafloor. So once generated, a tsunami will resemble a series of ripples that are formed, for example, when a pebble hits the surface of a pond. But in contrast to this example, tsunamis can advance as fast as 800 kilometers or even as fast as 950 kilometers per hour in open ocean. So that's as fast as a commercial plane, just to put it into perspective. That's how fast those waves can travel. Tsunamis, however, will start to slow down to about 50 kilometers per hour once they approach the shoreline. But basically, they can pass undetected in the open ocean, as the amplitude of the waves is usually less than 1 meter, and the distance between each of the wave crests, is between 100 and 700 kilometers, so a very large distance. But once the waves approach the shores and they kind of touch bottom or feel bottom, if you would, they will start to slow down again to about 50 kilometers per hour, and they will start to kind of pile up as the image on the slide kind of depicts. So you're seeing here that the crests are a lot closer together. They're starting to kind of pile up. There's a slow movement now, and so they become much greater near the shore. So the first warning of an approaching tsunami is often the rapid withdrawal of water from the beaches, which is a result from the first trough of the first large wave preceding the crest. So this would be the withdrawal of the water at the trough before the first large crest of the waves. So between 5 and 30 minutes, you'll see this retreat in the water before the large surge of water comes in. And this big surge of water typically can be capable of extending even up to several kilometers inland and causing much damage with it, obviously. So you may remember the tsunami of 2004 in Indonesia. I know I do. It shocked me when I was kind of young, but this earthquake of magnitude 9.1 caused a tsunami to hit the island of Sumatra, which claimed about 230,000 lives. There was also, a little bit more recently in 2010, the Tohoku tsunami in Japan. So the earthquake that caused it was a magnitude 9.1 earthquake, and it resulted in about 16,000 lives lost, 6,000 people injured, and about 3,000 people missing. So definitely nothing to not take care of, I guess. So before we leave here, I wanted to show you the video of how kind of tsunamis propagate. This is obviously a cartoon, but it's pretty decent at sort of displaying how that works. So you're seeing the megathrust over there. Let's go back a little. Okay, you're seeing the subduction of the slab, megathrust building up, energy slipping. There you go. That's the earthquake. Creates in the open ocean. Not much change, but once it approaches the shore, this builds up and it becomes great. Okay, so let's see. So in 1946, a large tsunami of about 15 meters struck the islands of Hawaii. So Hawaiian Islands, I should say. And these happened without any warning. This caused a lot of destruction in the Hawaiian Islands, which in turn motivated the U.S. Coast and Geodetic Survey to establish a tsunami warning system for the coastal areas of the Pacific. So those areas now include about 26 countries. So for this system, different seismic observatories in the area, so in the Pacific area, report any large earthquakes to the Tsunami Warning Center, which is in Honolulu. And then deep sea buoys equipped with pressure sensors check the energy released by an earthquake. There will also be tidal gauges that are measuring the rise and the fall in the sea level that accompanies these tsunamis. And usually within an hour, the warnings are issued. So based on all those different methods, these warnings can be issued within an hour. So areas that are more likely to get tsunamis are those around the Pacific Ocean, mainly, as you're seeing in the map on the left. They can also happen near the Indian Ocean, as you're seeing over here, like the Sumatra tsunami that I just talked about in Indonesia of 2004. And they can also happen relatively often in the Mediterranean Sea, especially here in the Greek islands, for example. Lastly, they can also happen here in the Arctic Ocean, next to, or at Russia, I should say, and Alaska. So, although the speed of the tsunamis is very high, there usually is enough time, sufficient time, for a warning to be made based on this method. So areas, for example, in the eastern part of the world typically will get a signal or some sort of warning from a tsunami or an earthquake that might have happened here in the Nazca Plate, for example, and it will be hours and hours before it reaches the eastern part of the world. And so typically there's enough time for warning, except when the earthquakes happen really close to the area that is trying to be warned, obviously. So about 95% of the energy that is released by an earthquake originates in a few relatively narrow zones. So these are shown in the figure on the slide, and these zones, you may notice, are also located along faults or fault surfaces where tectonic plates typically interact along one of the three plate boundaries. So the zone of the greatest seismic activity is called the Circum-Pacific Belt, and it encircles, for the most part, the Pacific Ocean almost completely, with the exception of the southern. With the exception of the southern margin over here. So for the most part, it's very seismically active, except for this southern part, and not as seismically active here in North America, although it's still somewhat active. Most of the earthquakes that occur in the Circum-Pacific Belt occur at the convergent plate boundaries when the oceanic lithosphere is subducted underneath continental lithosphere. So this is what's happening over here and over here, for example. And that's why you get the greatest seismicity, as well as here in South America, where the Nazca Plate is subducting. So it is in these areas of convergent plate boundaries where the oceanic lithosphere subducts under the continental lithosphere where you get the mega thrusts, which again are typically where you experience the toughest or the higher magnitude earthquakes, as well as the deepest earthquakes. So another major concentration of strong seismic activity is the Alpine Himalayan belt over here. And it runs through the mountainous regions that are next to the Mediterranean Sea and extends past the Himalayan mountains. So the tectonic activity that is ongoing here is mostly by the African plate and the Indian plate, which are both subducting or being basically collided against the Eurasian plate to the north of them. Transform faults that run through some continental crust are also a source of some of the larger earthquakes that we see. So that is, for example, what we see at the San Andreas Fault over here. But we also see it in New Zealand, for example, down here. And we see it also in the Anatolian Fault in Turkey, over here. So transform boundary with strike slip faults tend to be the second most damaging fault, aside from those thrust faults that are caused by the convergent plate boundaries. Lastly, we do see some seismic activity occurring all throughout the mid-ocean ridge system. So you do see some seismic activity occurring all throughout it, right? But as we said before, these tend to be minor magnitude earthquakes. So not as relevant, I guess, not as important in terms of damage that they can cause or energy that is being released. Okay, so here's a table that shows you some of the most or the more notable earthquakes in the last few centuries. In the table, you can see the year, the location, the number of deaths, the magnitude, and again, if they were able to calculate it then or later calculated based on records. And it also contains any comments such as the intensity scale as well. So I won't go through the table, but I do encourage you to pause the video and take a look at it. Also, the list only goes until the year 2016, as you can see. So if you want to look at more recent data, I would recommend you check other sources for it. Okay, so a pretty obvious question when we see the amount of destruction that the earthquakes can cause is, can earthquakes actually be predicted? And the basic answer is no. Definitely not on the short term, on the short range, and not precise enough in the long range. So let's start with the short range or short term predictions. So these short range predictions have a goal to provide the warning of the location and the magnitude of a large earthquake within a narrow time frame, so within hours or days, basically. So a lot of research in doing this type of predicting has been done in relatively wealthy countries where the earthquake risk is relatively high, such as Japan, China, and the US. Most of the research done has concentrated on monitoring of possible precursors to the earthquakes. So again, precursors are going to be events or changes that typically happen before the earthquake occurs. And thus, by monitoring these events, they could provide us with warnings. So things that are typically monitored are ground elevation changes, the variation in strain levels near active faults, groundwater level changes, the frequency of the foreshocks beforehand, and things like animal behavior, for example, by countries like Japan or China, which have tried to check the anomalous animal behavior in order to find some sort of pattern. However, this last one is pretty unreliable, so many scientists in the West have looked upon it with disagreements. Okay, so as far as current scientific investigations show, however, although these precursors may exist, we have yet to determine some sort of effective way in which we can interpret the precursors and also utilize the information that they give us in order to predict the coming earthquake. So, for a short-range prediction scheme to be generally accepted, there must be two things that happen. It must be accurate and it must be reliable. So overall, it must have a small range of uncertainty in regard to location and to timing. And it must produce few failures or few false alarms. So you can imagine evacuating a populated area will cost a lot of planning, a lot of money, and a lot of time. So some sort of short-range prediction must be able to avoid any false alarms or failures in order to avoid this costly event. So overall, with those aims in mind of being accurate and reliable, no actual reliable method does exist for making any short-range earthquake predictions, although precursor events have been monitored and tried to come up with some sort of method in which we can in the future predict them.